Hello, I am Tanzeel and I will be talking about the Ellis model. This is the model that have been given to me as the final presentation. So I'm gonna go ahead and start the presentation. First of all, it's the outline. So I'm gonna first talk about the Newtonian fluids and the models that are there for the Newtonian fluids and which are used to measure different properties of Newtonian fluids. And then I'll talk about the non-Newtonian fluids and then what are the models or what is the main model which is used for the non-Newtonian fluids. After that, and which is the power law. And then after that, I will talk about the power law and the Ellis model. What's the differences, how it's created, and then I will talk about advantages and disadvantages of the Ellis model, and then in the end, the usefulness of the Ellis model or in which circumstances or in which cases Ellis model can be used the best. So let me go ahead and next. Yes. So as most of us would know, the Newtonian fluids are simple fluids, and the main thing or the main property about them is that their viscosity remains constant with the constant shear rate, and there's a linear relationship between the shear stress and the shear rate. So the more shear rate you apply, the more shear stress you'll get. And as you can see in the graph over here, it's a linear and straight line. So that's what represents the Newtonian fluids. Obviously, if there's a change in temperature, there's going to be a change in viscosity. But if we consider just a constant temperature uh, and don't change the temperature, we will get this uh, straight linear line with in a graph shear stress versus the shear rate. If we change the temperature, it's gonna change the viscosity of the liquid. But then again, at the new temperature, if we keep that temperature constant, we will get the same results. So these are the Newtonian fluids, which uh, for which follows this rule and which follow this straight line when applied when they're under a shear rate. Uh, it's again I'm gonna talk a little bit more about Newton fluids and the model that is used. So it's called the law of viscosity, which is it says over here, shear force per unit area is proportional to negative of local velocity gradient. So as you can see, tau equals to minus mu dvx over dy, which is nothing more than just the shear rate. So it says tau is equal to minus mu shear rate, and it's basically stress versus strain. That's why we call it Newtonian fluids, because they follow these laws. And then what else we can do about this is, we have the law of conservation of momentum, so we can apply that, and by some substitutions we can end up with this equation. This is in terms, it represents the same thing. It's called the Navier-Stokes equation. It is made for Newtonian fluids as well. So Newtonian fluids, we can apply this to the Newtonian fluids, and it's applicable over there. However, these two models, they okay, the first limitation of these is that they are only limited to Newtonian fluids. We cannot apply these models to the non-Newtonian fluids. Second thing is that the change in the viscosity due to the temperature, this factor is not taken into consideration in these cases. So as we know that if there's a fluid and then we change the temperature, the viscosity of the temperature is going to change. But when we are using this equation, it does not take this into consideration. So we have to take a constant temperature and a constant viscosity, like we assume that it's constant. However, in reality it is not. And then the results we get based on these equations is their estimations. We can get the upper and lower limits and a rough estimation, but the values are not very accurate or not precise. So if for that we can go into further mathematical models to calculate those, but we can use these two simple equations to get an idea or an estimation of our liquid. Now next is the non-Newtonian fluid. So if you see on the left side, this is a Newtonian fluid. It's the same equation that we talked about in the last slide. However, it's the same similar thing in the non-Newtonian fluid. We can follow the same equation, but over here, this is the apparent viscosity, and it is not constant for non-Newtonian fluids. So as we know that there are different types of non-Newtonian fluids. So this is a graph of shear rate versus shear stress, and it shows the Newtonian fluid, which is a straight line which goes through it over here. Then we have two different types of, well, we have multiple different types of Newtonian fluids. The most common ones are the shear thinning and the shear thickening ones, and the Bingham plastic or Bingham pseudoplastics. Uh, as the name suggests, shear thickening, this means that as we increase the shear rate, the shear stress increases, which means an example of this is cornstarch in water. So if it makes it thick, if you mix it more, the more you mix it, the more thicker it gets, or more viscous it gets. And the opposite is the case in the shear thinning one, in which the shear, as you increase the shear rate, the shear stress goes down. So for example, if you see in a paint, if you stare, like this is a common practice as well, before painting on the wall or before painting anywhere, you mix or you stir the paint a lot so that it gets less viscous. As you stir it more, as you mechanically agitate more, as you increase the shear rate, the viscosity goes down, so that its wetting ability gets better, so it's easy to spread on the walls or where on any surface that you're trying to paint. So that is a shear thinning fluid, and it's a non-Newtonian fluid. So in those cases, we use this equation, which represents the change in viscosity, uh, and we use the power law. The power law is used for the non-Newtonian fluids because it gives a better estimation, and it takes into consideration this change in viscosity due to the shear rate, regardless of its increasing or decreasing. It takes into consideration, and then that's why we cannot apply the Navier-Stokes equation. We have the power law equation, which is required for the non-Newtonian fluids, and it just tells you over here that power law fluids are pseudoplastics, which are the shear thinning ones, for example paint, in which the viscosity decreases as the shear rate increases. That's what we talked about. And the dilatant, which is the shear thickening, in which there is an increase in shear rate with an increase in viscosity. Then there's the Bingham plastic as well, in which they are already at a higher stress before applying the shear rate or any type of shear. That you can say, for example, a toothpaste. It's when it's in a tube, it's under a stress, but it's not flowing. There's no shear rate. But as we start applying the force or shear, it starts coming out and it starts flowing. So that's one example of that. So I hope the Newtonians and non-Newtonian fluids, they are clear, and the differences are clear, and which equations can be used at what point. Now, at the end over here, it says the Ellis model fall in the category of generalized Newtonian fluids models. So when we were talking about the fluid models, we talked of three different models, and then one of them was GNF, which is generalized Newtonian fluid models. Uh, so it says over here the well-known GNF models are power law, uh, Carrier model, Herschel-Bulkley model, and Ellis model is also one of them. So I'm gonna be talking more about Ellis model now. Okay, so in the power law, so this the image. So I don't know why it switched like this. This text was supposed to be this text belongs to this image. This is for power law, and this is for power law, and this image, the one on top, belongs to the Ellis model, and it represents the Ellis fluid. So over here you can see that the velocity and the shear rate, the slope is over here is -1, and the bulk geology of power law fluid on logarithm scale for finite shear rates is greater than 0. So this is what represents the power law, and the bulk rheology of an Ellis fluid on the logarithmic scale, this is represented over here. So now I have another picture, I think a slide or two after this, which shows the same uh, similar curve where there is an elbow, and it says that where which part, or there is a left part, the lower plateau, where we can apply the Newtonian fluids, and there's the right side where we can apply the non-Newtonian fluid models. And then over here at this elbow we can apply the Ellis model. So we can, so this is representation of that. I will talk more about that. Now the Ellis model, this is how we represent the Ellis model. This is the Ellis model. Basically it's like it's equals to uh, eta naught over 1 plus tau over tau half alpha minus power raised to power alpha minus 1. Alpha over here is the measure of shear thinning behavior. It is the same as n in the power law of index, where alpha is greater than 1. uh, there's one thing I wanted to tell you. When we use Ellis model, I'll talk about it again in the end when I'll talk about the usefulness of Ellis model. But we use Ellis model where we have very low uh, shear. So in low shear rates or in low shear behavior, it is something that the Ellis model is useful, and we can get more appropriate answers as compared to the power law. uh, okay, and then over here tau half is this is the value of shear stress at which apparent viscosity drops to half of the shear viscosity. And it says for the material when the deviation from power law model is significant only in the low shear range. So that's what I was talking about. Low shear range where the Ellis model is more appropriate to use when we're dealing with low shear stress ranges. And if, so as you can see, if over here is tau is one by two or tau half approaches infinity, this model will transform itself into Newtonian behavior, because this whole thing will lead to the same model, same thing as Newtonian behavior tells us about. Also, if this whole term in the parenthesis, if this is much more than 1, like it's very greater than the value is much higher than 1, then this whole model reduces down to power law. So there's two things. If this whole parenthesis, or the tau by tau half power alpha minus 1, if this whole answer of this whole term is much greater than 1, or it's a very high value, then this whole model turns into the power law. However, if just this value, the tau half, if this approaches infinity, then this whole model like works as a Newtonian model or a Newtonian behavior. So there's these two things of Ellis model. This was a picture I was talking about earlier. That if okay, this is like I took this picture from the slides. So if this is it's a graph n by n naught, and this is the shear rate. Over here, when it's constant on this plateau, we can deal this liquid as a Newtonian fluid. We can apply those things, those equations. Over here and on this side, there's a power law or power fluid. At this elbow, where this elbow forms, where it transforms from straight horizontal line to a slope of -1, this we can apply the Ellis model, or we can deal it with this as a Ellis liquid or Ellis fluid. Now the advantages of disadvantage of Ellis model, the main or the biggest advantage, or why basically we use the Ellis equation or the Ellis model, is that it predicts Newtonian behavior at small shear stresses and the power law behavior at large shear stresses. So there's two parameters of this. If there's a very small shear stress, which is mostly when we use it, because we predict, then we can predict it back to the Newtonian behavior, and we get a good appreciation of that, or good appropriation of that. The second thing is the power law behavior if it's large shear. So when it's very low shear stress or very small shear value or shear stress is there, we can use the same model to have an approximation of the Newtonian behavior. If the shear stress is very high, then we can use the same equation to have an approximation of a power law. So it covers both of these, because so since it lies in the middle, it can go on the either left side or right side, but it covers both of these depending upon the circumstances, or depending upon basically the value of the shear stress. If the shear stress is high, it's going to act as power law. If the shear stress is low, it's going to act as a Newtonian behavior. Now over here, these three things, these are I wouldn't say disadvantages, but limitations of this. So the Newtonian plateau is dependent on the molecular weight and the temperature. So this whole things this whole curve is dependent upon the molecular weight and the temperature. And if temperature is not constant, we have to account for the change in tension and viscosity, which we don't, or we just say that it's constant in the, like it doesn't change. The second thing is in this plateau, it decreases with increasing PDI and a decrease in melt temperature. So there's two things: increasing PDI, we want to keep the PDI as low as possible to keep a better, to have a better quality, or a decrease in melting temperature. Both of these things, they will reduce this plateau, and then the lower this plateau gets, the higher for us, or the more difficult for us it is to apply this Ellis liquid or Ellis model. And then the last thing is the Ellis model, when we can use it. Or so it's a 3 parameter model. The power law is a 2 parameter model. So that's one more thing over here. This is a 3 parameter model that describes time dependent shear thinning non yield stress fluids. It is used, the most useful is as a substitute for power law, and appreciably better than the power law in matching experimental measurements. So it can act as a better approximation method when the shear stress is very high. Its distinctive feature is the low shear Newtonian plateau and without a higher shear plateau. The thing is that we can use it either in the low shear regime to get a Newtonian fluid, or at a high shear stress value to get the power fluid, or to get a approximation of power law. So these are the two usefulness of this model. So we can use this in either or, depending upon the circumstances or depending upon our needs. But it's a good approximation method, and we can get a good idea, like it we can get a better approximation of about the power law when we use the Alice model, especially in the higher stress areas. So this was it. Thank you so much. I hope this is uh, of some use to you, or you get something good out of it. It's just very simple, very basic uh, explanation of this model and then how it can be used. If you have any questions, you can email me. And it was a good semester. It was something. It was good to like to be in the class. It was obviously a different time, or difficult time, because of everything going on. But I think you handled it well, and it it was just good to be in the class and to learn all these things. So thank you very much.